Okay, good morning. So, this is lecture 9, I think it is, of computational complexity. And as I said, well, so as usual, we're going to have 2 hours of lecture, followed by student presentations starting at 10 o'clock. So as I said to those of you in the room before starting, a little puzzle to begin with is we've got 3 graphs, just ordinary non-directed graphs, and are there any isomorphisms between them or not? So has anybody managed to answer this question?
I would say the G1 and G2 are isomorphic, but they're not isomorphic to G3.
Okay, so did the rest of you agree with that, or have you? So G1 and G2 are isomorphic, and G1 and G2 are not isomorphic to G3. Okay, so very good. So can you convince me that G1 and G2 are isomorphic?
There's a mapping G1 to G2, so you can map so vertices in such a way that edges are preserved. So you can map.
Right. So that's what being an isomorphism means. So being an isomorphism means it's a one-to-one mapping from vertices, such that there's an edge in this graph if and only if there's one-to-one mapping between vertices. So there's an edge in this graph if and only if there's an edge between where the pair of vertices get mapped to in this graph. So to convince me there's an isomorphism, that these 2 graphs are isomorphic, you give me an isomorphism. So can you give me the isomorphism?
So 2 to 2.
So okay, so let's write it in this notation. So the isomorphism, the G1 is isomorphic to G2. So you're mapping 2, 2.
Then 4 to 3.
4 to 3.
Then I think that's 6 to 4 and 5 to 1. And then 3 to 5.
And 1 will go to whatever that which is set. Right, I'm checking that this is right. Do you agree with that? Yeah, okay, so this is the correct isomorphism. Well, this is, there may be more than one isomorphism here, I don't remember. Okay, and so G1 and G2 are isomorphic, but you said they're not isomorphic to G3. So how can you convince me that neither of these graphs is isomorphic to G3?
So 4 and 6 have 3 edges, and they are directly connected. Where in the other 2 graphs, only 2 and 4 have. So in the G1, 2 and 4 have 2 edges, but they are not directly connected. And in the case of G2, it's the same. So it's 2 and 3 have 3 edges going out of them, and they are not directly connected.
So 4 and 6 have 3 edges.
Yeah.
Okay, so there are 2 vertices that have rank of 3, that have 3 neighbors, and there is a connection between them. And all these graphs have 2 vertices that have 3 neighbors, but in these 2 graphs there is no direct edge between them. Okay, so indeed that's a good way of convincing me that G3 is not isomorphic to G2. Another one would be, so we'll have G2 is not isomorphic to G3. So another one is that G3 contains a 6th cycle, so the primitive basic 6 cycles and indecomposable 6 cycles. So is going down here, and these two do not contain any 6 cycles, but they contain a 5 cycle. So I'll write that one down. So G2 contains a 5 cycle. G3 contains a 6 cycle. So there were basically 3 things I wanted to, 3 points that I wanted to emphasize with these examples. The first one is just about how to see. Let's say you were thinking about these graphs and trying to see if the graphs are isomorphic. So how do we see if the graph is isomorphic? Well, when we do it ourselves, I don't know what you did, but you tend to look at the graph and sort of juggle it around in your mind, and it's a very visual exercise. So the fact that we're looking at graphs and we have a very graphical imagination here really helps. If you were a computer and you were trying to find out if the 2 graphs are isomorphic, you wouldn't get the graphs and pictures like this, and you wouldn't, well, you might nowadays with artificial intelligence, but anyway, never mind about that. In the good old-fashioned way of presenting graphs, one would present the graph like this as an adjacency matrix. So here are the graphs as adjacency matrices. And the question for the computer would be simply, is there a permutation on the 6 vertices such that the permutation takes this adjacency matrix to this adjacency matrix? So it's not such an easy question to answer from a computational point of view. There's no immediately obvious algorithm for that, apart from searching through all permutations. And searching through all permutations would be inefficient because that would be n factorial. That would take time, big O of n factorial, where n is the number of vertices. However, if we find an isomorphism, we can very easily communicate the isomorphism to somebody else. So you told me these 2 graphs are isomorphic. It's very easy to then back up that claim to convince me that it's true by showing me an isomorphism, by communicating an isomorphism. On the other hand, if 2 graphs are not isomorphic, well, again, you were able to communicate it, but there's not one simple uniform reason that 2 graphs might be non-isomorphic. So in this case, we had 2 different ways of looking at it, one in terms of cycles, one in terms of looking at the connectivity between the vertices of order 3 in the graph. So there were different ways of looking at it. But in general, you can imagine it might be quite hard to communicate why 2 graphs are non-isomorphic. For example, instead of having a graph containing a 5 cycle as opposed to a 6 cycle, so at least if something like that happens, you can communicate that fact to me, and it's possible for me to efficiently check if that fact is true, because checking for for a k cycle in a graph, it takes time polynomial in k. So a fact like this is possible for me to efficiently check. But for example, if you told me that one of the graphs contains a k clique, but the other one doesn't, which might be the reason that you see that they're non-isomorphic, it would not be possible for me to efficiently check that, because we know that a graph containing a k clique is an NP complete problem. Okay, so one of the main questions we're going to address today is there an efficient way of communicating facts like these 2 graphs are non-isomorphic, that you can convince me, is there a uniform way that you can always succeed in convincing me that 2 graphs are non-isomorphic, even if I only have efficient computational power at my disposal? So I need to verify that the 2 graphs are non-isomorphic in polynomial time. So what we're going to look at, let me put the board up. So today we're going to look at a little bit the graph isomorphism problem in general. So the problem of are two graphs isomorphic is an important combinatorial problem, and therefore an important computational problem, and actually has a very interesting computational history. So today it's lecture 9, and we're going to look at graph isomorphism. But in particular, of this question then, how can we communicate the fact, how can we convince somebody else or a computationally efficient verifier wants to check that what we say is true, how can we convince a computationally efficient verifier that two graphs are not isomorphic? It's easy to, if two graphs are isomorphic, it's easy to convince them that the graphs are isomorphic as we give them the isomorphism. But is there a uniform way of convincing the computationally efficient verifier that two graphs are non-isomorphic? And rather surprisingly and beautifully, it turns out that there is, but this involves a rather sophisticated notion, which is the notion of an interactive proof. So most of the lecture is going to be introducing you to the concept of an interactive proof. And the basic idea is somehow simple for interactive proofs, but the details of how it's defined are very subtle, sufficiently subtle that the textbook seems to get it wrong in several rather important aspects. So anyway, so we're going to talk about graph isomorphism and interactive proofs. Middle. So the graph isomorphism problem is simply the problem. The input is take two graphs, there's two graphs, and the output is, well, yes, if the graphs, accept if the graphs are isomorphic, reject if not. So we know how to present graphs as adjacency matrices. I've got explicit examples up there. So the graph isomorphism problem. So the input is two graphs, G1 and G2. And the question that we will accept if it's true is simply, are G1 and G2 isomorphic? And we want to know, well, the first thing we would ask ourselves is there an efficient algorithm for this? So if there's an efficient algorithm for this problem, we don't really need to worry about communicating whether or not two graphs are isomorphic, because if there's an efficient deterministic, say, algorithm, then we don't, we just need to give the graphs and the verifier can verify it for themselves efficiently. So if there's an efficient algorithm, then there's nothing much to say. So you can guess that nobody knows, well, you can guess that we don't have an efficient algorithm. In fact, nobody knows if one exists. So I'll come to that in a moment. But just to say, well, we're inputting two graphs, G1 and G2. Of course, if they have a different number of vertices, then they can't be isomorphic. So we might as well assume that they have the same number of vertices, and occasionally that will be convenient. I'll just put that in brackets because it's not really important. It's the sort of assumption one can make for convenience sometimes. So that's the problem. Of course, as always, we can define it as a language. So let's define it as a language. So as a language, it's called GI. This is one of these famous, standard famous languages in complexity theory, like SAT is the language satisfiable formulas. GI is the language of graph isomorphism. And so it's the set of words where a word is in the set if it is a word that represents a pair of graphs and those two graphs are isomorphic. So it's the set of those words that are pairs of encodings of a pair of graphs, G1 and G2. So remember, this just means an encoding of a pair as a string, and G1 in these little corner hats is these little corner quotes means the encoding of the graph G1 and the encoding of the graph G2. So for example, as adjacency matrices, and the language is simply G1, G2 are graphs, just ordinary undirected graphs, I mean here, and G1 is isomorphic. This is the symbol for being isomorphic to G2. That's right. I was already using it earlier, but just emphasize this means isomorphic. And by graphs, for this problem, we're talking about simple undirected graphs. So there's no orientation to the edges, and there is no edge from a vertex to itself. Not that the problem changes significantly if you allow it to be vertices from edges to itself, from an edge to itself. Okay, so this is the language of graph isomorphism. So again, we're going to be in the situation that I would like to push this board up, but never mind, we just have to live with the boards as they are. We're also going to look at essentially the complement language, GNI, graph non-isomorphism. So the actual complement language, as the complement of the set of strings, would be simply all those strings that are not of that form. The interesting language to look at is the set of strings of those pairs that are graphs, that represent graphs where the two graphs are not isomorphic. And it's easy to go from the complement to GNI and from GNI to the complement by reductions. In one way, you just weed out those strings that don't represent pairs of graphs in an interesting way. You just check the string to see if it represents a pair of graphs. You did that sort of thing in exercise classes a few weeks ago, so we're not going to worry about that. So for our purposes, GNI is going to be the set of pairs of graphs G1, G2. Or again, we could restrict to graphs of the same size if we want to. So let me put that in brackets because I might use it if helpful. G1, G2 are graphs. So put it of the same size, which means the same number of vertices. So I don't know in the official language GNI whether or not this is there. Doesn't really make much difference with the same number of vertices. To any interesting question, it doesn't make any difference. Okay. The GNI, so that's the language pairs of graphs that are not isomorphic, and GNI is essentially the complement of GI. So as I said, the actual complement is just all those strings of the alphabet we're using that are not of the form a pair of encodings of graphs that are isomorphic. But one can go from that language to GNI and back again very easily just by checking whether or not the input is indeed of the form of a pair of graphs. And so for interesting purposes, one can think of GNI is essentially the complement of the language. Okay, so I'm afraid I'm going to cover this board straight away because it'll take a few seconds just for the board to come down. There's no way of making that visible. So let's do some properties of this problem. So the first question would be, if it had a positive answer to it, we would be happy with the situation, and then this actually problem would not be so much under discussion as exists today. But the first question is, does the language of graph isomorphism have an efficient algorithm for it? So there is language of graph isomorphism. Is it polynomial time computable? Is GI in P? But nobody knows. But this is an open question. So it could be, and it's less of an open question. I mean, whereas everybody believes that SAT and NB complete problems, most people believe they're not polynomial time computable. I think with graph isomorphism, there's no consensus about what everybody believes. There's some. One could imagine that by doing some clever statistics of a graph or something like that, one could be able to. One could always distinguish two graphs by collecting the right clever statistics. So there's that sort of question, and there's a lot of research about this. But anyway, is this even the right open question now for graph isomorphism being efficiently computable? Because last week we introduced randomness into our model of computation, and for all intents and purposes, bounded probabilistic polynomial time algorithms are just as efficient and useful as deterministic ones. So actually, even if GI is not in P, maybe the right question for is it efficiently computable is rather, let's be a bit more liberal, and maybe it belongs to BPP. Bounded probabilistic polynomial time. But again, that's another open question. Well, what can we say that's positive? Well, we do know that graph isomorphism, if two graphs are isomorphic, you can convince me that two graphs are isomorphic by giving me an isomorphism. So what does that tell us about the BPP problem? Which complexity class do we know that it belongs to?
NP.
It's indeed, it belongs to NP because giving the isomorphism amounts to giving a certificate that the two graphs are isomorphic. So we do have, we do know that GI belongs to NP, because an isomorphism is a certificate. Hence, what does this tell us about GNI, the language that two graphs are non-isomorphic? So graph isomorphism belongs to NP, so where does the problem that two graphs are not isomorphic belong? Cool. Co-NP, very good. It's the complement, it's computationally equivalent to the complement language. So this belongs to co-NP. So graph isomorphism is an NP problem that is not known to be polynomial time, like SAT, like all the NP complete problems. But I said that many people are more inclined to believe that graph isomorphism is polynomial time than are inclined to believe that SAT is polynomial time. So one way of giving some rationale to that point of view is asking, is GI potentially NP complete? And there is actually quite a lot of evidence that GI is not NP complete. As always with complexity theory, it's hard to get absolute negative results. So it's we can't show that SAT is not polynomial time, at least we haven't found a way to do it. That would be showing that NP is different from P. So people believe that GI is not NP complete, which in itself implies that P is not equal to NP, because if P equals NP, then every NP problem is NP complete. But what we can show is that there's a complicated argument that if GI is NP complete, then remember in the exercise classes, you did the polynomial, a little bit about the polynomial hierarchy, so the sigma and pi classes that you were looking at those using classes of quantified Boolean formula. So if graph isomorphism is NP complete, then it turns out that polynomial hierarchy collapses. So this has been proved in the sense that the level 2 of the polynomial hierarchy, it collapses at level 2. So the sigma class is the same as the pi class. So i.e. polynomial hierarchy collapses, as people say. So people take this as strong evidence, the best evidence we can have with our current ability to prove things in complexity theory. This is really the best evidence we can have that graph isomorphism is not NP complete. So this is strong evidence. GI is not NP. And there's one other thing that's, well, lots of results are known about special classes of graphs. So actually, for lots of special classes of graphs, like you consider graphs like planar graphs and things like this. I don't actually remember for which special classes this is known, so maybe it's not true for planar graphs, but I expect it is. But actually, for lots of special classes of graphs, it is known that graph isomorphism is in polynomial type. But the best result that's known for general graphs was a rather celebrated breakthrough result from quite recently, so 5 or 6 years ago, 2015. Although it originally had a mistake in it, so it was only corrected in 2017. So there's a recent celebrated breakthrough. Which shows that graph isomorphism is in a class of deterministic algorithms that is strictly included in X time. So it belongs to NP, and the best we know for NP algorithms in general is that they belong to X time. But actually we can do better with graph isomorphism and find a much better bound than a general X time bound. And this is called a quasi-polynomial bound. And so this result says, I need to look at my notes for this. So this result says that the graph isomorphism problem is a deterministic algorithm for it. And this would be a whole course to present this algorithm. It uses very, very sophisticated mathematical methods, mainly based on group theory. So there's an algorithm that is an exponential, but it's not an exponential 2 to the n, it's 2 to the power of a polynomial in the logarithm of n, of the size of n. So graph isomorphism is in d time, actually let's not make it 2, let's make it c times log n, and this is cubed, yeah. Sum c greater than 1. Or an equivalent way of writing this c times 2 to the power of O log n cubed. That's the same thing. So this result is by 2015 and then 2017. And the 2017 was in response to an error being found by Helfgott. So it's a very complicated algorithm. I had a long preprint in 2015, and then Helfgott found an error in it, and then I managed to correct it. So if you didn't have the cubed here, so c to the log n is of course linear in n. So the idea here is we're being exponential in a polynomial of the logarithm of n. Such a thing grows in general faster than any polynomial, but more slowly than any exponential, more slowly than 2 to the n. So let me just mention briefly what the terminology is for this. So this says that GI has what's called a quasi-polynomial solution. A quasi-polynomial type algorithm. And in general, we could define, for what it's worth, let's define the complexity class of quasi-polynomial time. So that's the union over all polynomials of d time 2 to the p log n. So, exponential in a polynomial of the logarithm of the size. Okay, so these two results here, let me put these ones in. These two results that I'm circling in red, this one and this one, are both very significant results that would take a more advanced course to prove. So we're not going to look at those proofs. I mean, this is, I don't know how many people have really digested this, algorithm here at all. Anyway, what we're going to do instead is, after the break, go and look at the little thing we're going to talk about, which is how to communicate. We know graph isomorphism is an NP problem. We know what a certificate is, so we know how to communicate to somebody else with only deterministic polynomial time available that can, so someone could efficiently check any claim we make that two graphs are isomorphic. If we claim two graphs are isomorphic, what we're going to look at is a way of being able to communicate that two graphs are non-isomorphic. So going back to the question we started at the beginning. Okay, so I think we'll break now and start again at 1 minute past 9. Oh, 2 minutes past 9. I'm just, are there any questions? No, okay, I shall pause the video. How do we pause? Yeah. Okay, so in the first part, we looked at some results. I just stated them for the graph isomorphism problem. Now I want to come back to the main issue that I raised at the start, which is if somebody knows that two graphs are non-isomorphic, is there a way they can communicate that to convince a verifier, someone who wishes to verify the claim that the two graphs are isomorphic, where the verifier is only going to run some uniform, efficient algorithm to verify the claim that the two graphs are non-isomorphic. So if two graphs are isomorphic, it's easy to communicate the fact to convince somebody else that two graphs are isomorphic, because we just communicate an isomorphism. Is there a uniform way of communicating the opposite fact that two graphs are not isomorphic? So let's have a look at how this works. And I'm basically going to present the solution. And once we've understood the solution, we'll then make a general definition based upon it. Making the general definition is surprisingly simple. It's not completely straightforward to turn the idea. The idea is natural, but it's not completely straightforward to turn that idea into. I'm going to shut the door. If you want some more air, please open the window. It's not completely straightforward to turn the idea into a mathematical definition. Let me just clean the board first. So let's put ourselves in the position of wanting to be convinced. We've got two graphs in front of us. Somebody tells us that the two graphs are not isomorphic, and we want them to convince us of this fact that the two graphs are isomorphic. So we're going to put ourselves in the position of what we're going to call the verifier. We're going to verify that two graphs are non-isomorphic. So, let's consider how we might verify a claim made by somebody else that two graphs are non-isomorphic. And we don't just want to verify, we want to efficiently verify it. Efficiency is important here because if we gave ourselves arbitrary exponential time, then we could just go, or super exponential time or whatever, we could just go through all the permutations of on the set of vertices and check to see if there was any isomorphism. Just check that there was no isomorphism among them. So it only becomes an interesting question if resources are limited, but in the real world they always are. We don't have an arbitrary amount of time at our disposal. So what we're going to do is we ask the other person to prove to us that the two graphs are isomorphic. So we ask the other person to prove to us they must do so in such a way that they don't demand more resources than we've got. So they can't force us to do an exponential amount of computation. We want to efficiently verify. On the other hand, the person that's proving, we can imagine that they potentially know things that we don't know. I mean, they know that the two graphs are isomorphic. They presumably have some reason for that, and they should be able to tap into that reason and use that reason to be able to convince us. So we're not going to put any bounds on the resources of the prover. So we're going to have, so our verification is going to be, I mean, the idea is the prover is going to try to communicate to us some reason as we ask it for this fact to be true. And we're going to allow ourselves to question the prover. So the prover will say something, and based on that we might ask the prover some other question, and there's going to be some interaction. So the thing that's going to change with respect to just giving a certificate for an NP problem is that a certificate for an NP problem is simply the prover gives us the certificate and says, there you are, and we go ahead and check the certificate. What we're going to change from that is we're going to allow ourselves to ask the prover questions. So it's going to be interaction. So we're going to formulate this. Formulate the resulting protocol. Interaction between us verifier D and a prover D. The important thing here is going to be interaction. This is why such a thing is called an interactive proof. So, as I said at the beginning, today the subject today is interactive proofs, and it involves an interaction between us, the verifier, and the prover P. So for us, efficient computation required, and for P, there's no resource bound. So I'll make these technically precise later. Well, there is some resource bound on P, but not a significant one. Okay, so we're going to look at now the interactive proof for graph non-isomorphism. So, interactive proof in which prover P is going to convince the verifier convinces the verifier V, I don't need to write out all the words, that two specific graphs we're dealing with are not isomorphic. And the whole thing is based on an interactive protocol. We can ask the proof, we're the verifier, we can ask the prover questions, and the prover needs to convince us indeed that graph 1 is not isomorphic to graph 2. Now, beforehand, I mentioned things like the verifier, you can imagine the prover might tell us, well, in this graph there's a 6 cycle, and in that graph there's a 7 cycle, or something like that. And that would work in a handful of cases, but would not be a general reason for two graphs being non-isomorphic. So the difficult thing we need to address here is find a uniform method that will always, no matter what the graphs are, as long as they're not isomorphic, will always work, and will always be able to convince us that the two graphs are not isomorphic. And it's going to be this interaction between the verifier and prover. Because it's an interaction, we're going to write it out a bit like a script for a play, where each player plays their role, and we say, so actually this is going to start with verifier. So it's now the part of verifier on the play. So verifier enters the scene. And what verifier does in that term is verifier randomly chooses one of these two graphs by tossing a fair coin. So the verifier tosses a fair coin. And I number 1, 2. So basically, with probability half it comes up 1, with probability half it comes up 2. It then generates a random permutation. So we're only interested in the case that G1 and G2 have the same number of vertices, otherwise we're already convinced they're non-isomorphic. So where G1 and G2 have n vertices. So we choose one of the two graphs at random, and then what we're going to do is randomly commute it. So we choose a random permutation, sigma, let's call it, from n to n, where my square brackets n, this is just a short notation of a set of numbers 1, 2 through to n. So it's easy to choose a random permutation. You just randomly generate a number between 1 and n with uniform probability. You've then used up one of the numbers, and you've got n minus 1 numbers left. You then randomly choose a number between well, you randomly choose one of the n-1 remaining numbers with uniform probability. You've then given your first two places of the permutation, and you've got n-2 numbers left. You randomly choose. Anyways, it's easy to randomly choose a random permutation with uniform distribution over permutations. Let's just be precise. So with uniform distribution over permutations. But anyway, one can do this easily. And now, having done this, we do this behind our backs, so to speak. We don't show this to the prover, but we're now going to give the prover some information. And the information we give them is we randomly commute the graph GI that we've selected according to sigma. So we apply our permutation sigma to GI. So we pass the V passes prover P the graph which I call G3, which is the permutation sigma applied to the graph GI. Very importantly, the only information that is passed to P is the graph G3. So that's just the adjacency matrix that we get by applying the permutation to the graph GI. So from that, the prover does not see sigma and does not see I. They only see the adjacency matrix. So the P, put this in red, P receives only the adjacency matrix. And now it's P's go. And what P does is P's turn. So P gets the graph G3. So P now has three graphs to look at: G1, G2, and G3. And all we know about G3, all that P knows, is that it is a random permutation of one of the graphs, G1 or G2. So it will be isomorphic to one of G1 or G2. So P checks to see which of the two graphs it's isomorphic to. So if G1 is, if G3 is isomorphic to G1, of course it doesn't matter what order we write it, but let's put it this way around. If G3 is isomorphic to G1, then P sends the value J. So it sends the value J to V, and that value is 1. The idea is P is going to try to tell, so P is basically going to guess I. That's what it's trying to do from the information it's got. The only information it's got is the graph G3. But it can guess I because it just checks to see, it's got a graph that's isomorphic to one of G1 and G2, and it can only be isomorphic to one of them because they're non-isomorphic graphs. So it finds out which one it's isomorphic to, and that must have been the respective value I. So if G3 is isomorphic to G1, and if G3 is isomorphic to G2, then P sends J equals 2. So remember, we hadn't bounded the resources of P. We allowed P to be very, very clever. And so P's looking for isomorphisms. We don't know how to do that efficiently, but that's the prover. That's not our business. On the other hand, we are going to have to wait for P to give a response. So the question is this sort of thing really practical? And in many ways, it's not. But in some ways, it's not so unrealistic. Because if P really knows to begin with, as they claim to, that G1 is not isomorphic to G2, P should have some reason that G1 is not isomorphic to G2. But in fact, what P1 can do here is check that reason with respect to the pairs G1 and G3 and with G2 and G3. And if P finds that G1 that G2 is not isomorphic to G3 for the same reason that G1 was not isomorphic to G3, then P can conclude, well, in that case, G1 must be isomorphic. If G2 is not isomorphic to G3, then G1 must be isomorphic to G3. So actually, P in practice doesn't need to do a search for an isomorphism here. P can apply their reason for knowing that G1 and G2 are non-isomorphic in order to find out which of these two branches it falls in. From our point of view, we just send, we verify. We send the prover this information, this graph, and we wait for the response, and we don't actually need to worry too much about what P is doing. And then at the end, we get back the J. And what we want to do is we're going to accept if, so we're essentially asking the prover to guess I, and the prover sends back their guess for I, which is J, and we're going to accept if the prover sends back the correct J, and reject if the prover sends back the incorrect one. So B is going to accept if J equals I, and reject if J is not equal to I. So, order. So let's look at some properties of this protocol. Because it's actually a little bit subtle how this is working and what it's doing. So, so I was assuming that P really is trying to convince us that G1 is not isomorphic to G2 in the case that G1 and G2 are really not isomorphic. So let's start with checking that we at least accept in that case. So if G1 is indeed not isomorphic to G2, and if P behaves in the way that we're saying it should behave, and if P behaves as specified, then the probability, so because we've got so many P's around, we've got P for the prover, for example, and P for the complexity class, I'm going to use PR for probability now. I was using just P, I think, last week. But then the probability that V accepts is 1. Because if the two graphs are really not isomorphic, then only one of those two if clauses can be right. G3 has to be isomorphic to exactly one of G1 and G2. And we'll return the respective J, and that will be equal to I. So that's the easy case, so to speak. More interesting case is actually the point of this is we want to be convinced at the end that the two graphs are really non-isomorphic. So we have to be open to the possibility that they could be isomorphic, in which case we don't want to be convinced that they're not isomorphic. So we need to make sure that we're going to reject in the case that we have two graphs that
that fail to be non-isomorphic. In other words, if we have two graphs that are isomorphic, we want to reject. Only things are a bit probabilistic, so we want to at least, we've seen similar things last week, what we're going to do is bound the probability that we wrongly accept in the case that two graphs are isomorphic. So in the case that two graphs are isomorphic, then what I claim is what we want to make sure is that we can't be wrongly convinced that two isomorphic graphs are non-isomorphic. So we want to check that if two graphs are isomorphic, we're going to reject with sufficiently good probability. And moreover, we want to make sure we do that no matter what the prover does. We don't want the prover to be able to cheat us, to lead us to believe that the two graphs are non-isomorphic when they're not. So the appropriate thing to say here is we don't assume that P behaves as specified, but no matter how P behaves, we're going to show that we reject with a sufficiently good probability. So if G1 is isomorphic to G2, then no matter how P behaves, as long as it returns, P has to return a J equals 1 or 2, but no matter what algorithm it applies to do that, so no matter what it does, then we're going to have the probability that P rejects, which is in this case we want to reject because the two graphs are isomorphic, not non-isomorphic, is a half. That's what I claim. So this is a slightly subtle point. We now don't know how P is behaving. So why is this? Well, suppose the two graphs are isomorphic, then we randomly choose one of the two graphs and send a random permutation of that to the verifier. But a random permutation in this case of G1 is indistinguishable from a random permutation of G2, because G1 and G2 are isomorphic graphs, so they have the same distribution of permutations. The permutations of G1 are the same thing as the permutations of G2 because they're isomorphic graphs. So the crucial points here are permutations of G1 are the same as the permutations of G2. So from G3, when the prover gets G3, all it will get is a random permutation of G1, which is the same thing as a random permutation of G2. So from its only input, G3, P gets no information about I. Because whatever I is, if it's 1 or 2, P gets the same inputs with the same probability distribution. So in that case, whatever value P returns, whatever algorithm it's applying, whatever value J it returns is going to be independent of I. Okay, so the value J returned by P is independent of I. That's great. So we have the probability that B rejects. It's the same thing as the probability that, well, B rejects if J is not equal to I. So the probability that J is not equal to I. The J is independent of I, and I was chosen with probability of half, so that's equal to I, irrespective of what. So the independence is used in this equality. Okay. So it's a little bit subtle. And then, how can we actually use this? I mean, we've still got the probability of a half of going wrong. But following on from last week's lecture and exercise class, you can imagine how we're going to reduce the probability of a half of going wrong. So using repeated rounds, we'll say a round of interaction goes from verifier to prover back to verifier. Using repeated rounds, we reduce the error probability. So let's do this in the case of 2 rounds, and then I'll stop at 2. So e.g. in 2 rounds. So the way this works in round 1, then we're going to just run the protocol that we did of asking the prover to tell us to guess the I that we're guessing. So in round 1, we have V chooses I1 and sigma 1. So it chooses which graph to send to permute. It chooses its permutation and sends the sigma 1 of G of I1. And then P returns J1. And then rather than accepting or rejecting at this point, we go into round 2 and we ask P again. So now in round 2, P simply does the same thing. So this time it's going to choose I2. So again, we randomly choose a graph. And then we randomly commute it. We send B, so we choose I2, sigma 2, and sends the permutation of GI2 in this case. So again, we randomly choose a graph and commute it. And then P will try to guess I2. So P returns J2. And then to finish, what do we do? So in this case, we're going to accept if the prover guesses right in both cases. So B accepts if he guessed right in the first case, so J1 is I1, and it guessed right in the second case, so J2 is I2. So using and there, and we're going to reject if V got it wrong. Because if V is behaving in the way it's supposed to behave, then, and the graphs are really non-isomorphic, then V will get it right every time. Sorry, P will get it right every time. P will guess the right I every time for its value J. So V rejects if J2 is I2 and sorry, this is what I meant to say. So if one of them is not equal, so J1 is not equal to I1, or J2 is not equal to I2. to the properties of the two-round protocol. Again, if we have isomorphic graphs and P behaves and the prover behaves in the way it's supposed to, well, it will guess the correct I both times with the probability that B accepts is 1. If instead we start with isomorphic graphs, then for the same reason as before, then each time the prover will have a 1/2 probability of guessing the wrong J. And so each time there's a 1/2 probability of P getting it wrong, no matter how it behaves. And therefore, there's a 3/4 probability that we shall reject in this case, because there's a 1/4 probability that it will get it right on both occasions. So the probability that B rejects is 3/4 there. For the same reason. And if we're in K rounds, you can imagine generalizing this to K rounds. And the probability then is 1/1 minus 1/2 to the K. So by playing K rounds, we can make the probability, no matter how P behaves, we can make the probability that we reject when two graphs are isomorphic as close to 1 as we like. Okay. Right, are there any questions on that? It's quite subtle.
This is kind of similar to the zero knowledge proofs in cryptography.
Yeah, well, the zero knowledge proofs are based on this. So you've done zero knowledge proofs in cryptography.
Well, I didn't, but I read about them.
Right, so we will do zero knowledge proofs next week. And, right, so indeed this is. So just to check, you haven't done these interactive proofs in some other course, have you? Or no? Okay. So hopefully the idea here of what's happening for graph isomorphism is quite straightforward. So now, based on this, let's keep it in mind. And now we have to take the remaining 10 minutes to give the general definition of an interactive proof. This is a specific definition, I mean a specific example. The general definition is a little bit complicated. So the ideas are simple, but the general definition is quite complicated. And it's sufficiently subtle that the textbook makes at least 2 fundamental errors in the Aurora and Barrett textbook. Okay, so what I want to think about is, so here we've got a very specific verifier, and in the end, well, we considered to get for the prover to convince us of a non-isomorphism, it needs to behave in a certain way, but even if it tries to mislead us, it can't convince us that 2 isomorphic graphs are non-isomorphic, however it behaves. And, well, only with very, very small probability, we can make that as small as we want. So we're going to have the similar thing. So what we want to do is say that rather than work with a specific verifier V, we want to consider what an arbitrary verifier V would look like. So interaction between V and P in general. So we want V to be given by a probabilistic Turing machine. and we want P. For the moment, we can just think of it as an arbitrary function on the alphabet, because it doesn't need to be given a priori, even by a Turing machine. The prover might pray to God to get some information or something like that, and that would be fine by us. But notice here I'm making it a function, so there's no probability built in. We could add probability, but adding probability will just make the definition more complicated and actually doesn't give us any more power. Doesn't give any more power. So we might as well at least simplify lives a little bit by making P deterministic. So a k-round interaction on an input W belongs to sigma star proceeds as follows. So firstly, V goes first. See how I've written it. The V computes its first message, V1, little v1, by running the Turing machine V on W. So this means run V on W and wait to get some output. And V passes V1 to P. So P computes its reply, P1, and that's obtained by applying P to the function W hash. So I'm assuming that hash is kind of in the alphabet for the P, but is not used elsewhere in this. I mean, one can be very careful about the alphabet and how one's dealing with it, but I don't want to fuss over such details. I just want to chain W. So the point is that the prover gets past the input string W together with the message V1. Okay, so V1 here is the random permutation of the graph in our previous example, and P1 here is the value J that the prover returned in our previous example. And then we go into round 2. If we have 2 rounds, we might not. But if we have 2 rounds, then V will compute V2, which is obtained by running V on the input W together with V1. We remember the whole history and together with P1. So we're interacting with the prover, so we look at what the prover sent us and we use that as input to what the verifier is going to do, potentially in the next round. We didn't actually need that information in the 2 rounds we had before, but in general we could allow ourselves to use all the results of what's happened before in our second round. And then P computes a reply to that. So when I say computes, maybe the P is not even assumed to be a Turing machine, so produces, let's say. So again, we're going to get P2 by applying the function P to the input string and all the information that's available to the prover at this point, which is the initial input V1, the prover's own response to it, and the new input V2, and so on. And then we go to K rounds. So on the kth round, we have V computes another message, VK, the kth message to pass to the prover, which is V applied to W. Sorry, this should be P1 here. So we give it all the information that's taken place in the discourse so far. So all the way through to vk minus 1 and little pk minus 1. And P produces PK, which is getting a bit tedious to write it all. And lastly, at the end, after k rounds, so here we have round 1, here we have round 2, we have round k, and at the end, what we require at the end, the interaction finishes in case that if, in the case round, rather than outputting a value on the output tape, this Turing machine for V instead goes into either the accept or reject state. So V computes either, so again, we apply all the information so far. So we've got the original input word, we've got the whole protocol, the messages we pass to the prover, messages that the provers pass back to us for all the k rounds, and we go into either an accept state or a reject state, and then the protocol finishes. So we require that to happen. Right, so it's already 10:02, but we've got 2 shorter presentations today because we've got 1-person presentations rather than 2-person presentations. I'm going to make the final definition now, and then that will be the end of the lecture, and then we'll have the full 10 minutes break. But I need to go on for another 5 or maybe 10 minutes to finish the definition. So let's put this up. So, the definition, the complexity class IP, languages with interactive proofs. Languages with interactive proofs. So L is in IP if there exists a verifier that can interact with the prover for the prover to be able to convince the verifier that the word belongs to the language. So if there exists a verifier, and we require, in this case, our verifier needs to be efficient. So I didn't say efficient before, but now we want to make it efficient because we're talking about a complexity class. So we're going to require an expected polytime, an expected polynomial time, polytime, probabilistic Turing machine D. Such that two properties hold. So probabilistic is very important here because it's probabilistic. We want it to be polynomial time. It's natural to say expected polytime, but like in the exercises last week, it doesn't make any difference if you say worst case polynomial time here. So such that two properties hold completeness, and this means there is some prover that will, such that the verifier will be able to, with that prover, with some prover that can convince the verifier with high probability that a word is in the language. So completeness is there exists a prover, such that for all words belonging to the language, the probability so I want some notation here. The value that we get at the end from the prover, let's use orange for this. This value here that we get from the prover, this is the result of the interaction between V and P. So I'm going to call this out, the output, the result of the interaction between V and P. Let's see if that's, yeah, that is, I did just manage to get it on Zoom, so on the video. And what we want here is the probability that the output of the protocol, so there is a verifier such that there exists some prover that will convince the verifier that W belongs to the language. So I think I put V first. So the output of that, the probability that the output is accept for a word in the language. Well, before in our example of graph non-isomorphism, that probability was 1, but just like with bounded probabilistic polynomial time, it's enough to make the probability high enough. So we'll make this greater than equal to 2/3. The soundness is that we can't be convinced of an incorrect, we can't be convinced that a word's in the language if it's not, at least only with low probability. There's a very low probability of being convinced that a word in the language is not. And we want this to be the case. We don't want, even if the prover lies to us, we can't be convinced that, even if the prover doesn't behave in the way we think it's behaving, we can't be convinced that a word is not in the languages. So in this case, we want to go over for all provers and for all words in the language, the probability that the result of the protocol is reject. Again, this type, if we're a word, sorry, this should be all words not in the language. The probability of rejecting the word is high, is greater than equal to 2/3. And as before, we can boost these error probabilities, well, sorry, these are correctness probabilities here. We can make them as high as we want by running the protocol many, many times and doing exactly the same sort of thing that we did in the exercise class last week, they are the majority. The two remaining things to say about this. This is for exists P for all P means for all. So where P ranges over all possible provers with respect to our verifier V. So what does it mean to be a prover? So P is a function, but we want it to behave we want the function to actually act as a prover function with respect to V. So to complete the definition, P is a prover with respect to V if, well, so P is a function on strings. So it doesn't need to be given by a machine. If two things. So firstly, P must not explode the string it must not blow up the string too much. It can't do an exponential blow up in the string, because in that case, we would then, our probabilistic time verifier would then get very large inputs and would be able to do anything. So P has only a polynomial bounded size increase on strings. So I won't write this out mathematically, but I hope at this stage in the course you know what I mean. So there exists some polynomial such that for any input string W, P of the length of P of W is less than equal to the polynomial applied to the length of W. Okay? And the other thing is that the interaction of P with V halts in polynomially many rounds in the size of an input string W. And P would be on input W in polynomially many rounds in W, the size of W. So the interaction is as defined on the board at the top there. V passing, V computing the first message to pass to P, P computing the next thing back, and eventually, in only polynomially many rounds in the size of V, of W, the input W, we have to get to the stage that V will eventually go into an accept or reject state. So it will conclude the protocol. So I think you will hopefully agree with me that from this one example, and there will be another example in the exercise class, but the one example shows it's quite a natural idea, and the idea is reasonably intuitive. When you try to formalize it, it becomes quite complicated. And so the two crucial mistakes that the textbook made, unless I missed them, it didn't make this polynomial bounded size increasing restriction in the textbook. And even worse, I mean, that's bad, but that's like an oversight. But even worse than that, it got these quantifiers in the wrong position. And it's very important that they're in this position here, this exists and for all P. So an intuitive notion, but one of those notions that is actually quite hard to pin down mathematically, but this is hopefully the correct definition. So we now have a new complexity class of languages. And do any of you know what the big result about interactive proofs is? Do any of you know offhand? So, big results. So we've shown that this co-NP problem of graph non-isomorphism has an interactive proof. Actually, it turns out that a huge number of problems have interactive proofs. It's a very surprising result. And the big result is that IP is equal to P space. And this result is going to be the subject of the lecture in 2 weeks' time. Today's the 6th, so I guess the 20th of December. So this will be the lecture of 20th of December. That's because that's going to be a technical proof, and there's not going to be it's not going to be appropriate to have an exercise class associated with that. Next week, we're going to do something else based on interactive proofs, which is to go and look at a little bit of cryptography and the notion of zero knowledge proofs. And there'll be an exercise class following that. Right, good. So sorry for overrunning. It's 4 minutes past. We'll have a 10-minute break till 1/4 and then we'll have the student presentation. But that's everything for the Zoom now. So I'm going to stop the recording and say goodbye to people that are on Zoom.